When people first learn Linux, they often think of a user account as a name you type at login, but the operating system thinks in a deeper and more consistent way. Linux treats identity as a set of numbers and rules that determine what a process is allowed to do, which files it can access, and which actions it can take on the system. That means user and group concepts are not just administrative details. They are the core language Linux uses to enforce security and order. You might see a username on the screen, but the kernel and the file system are using identifiers behind the scenes to decide whether an action is permitted. This topic matters on Linux Plus because many questions are really permission questions disguised as something else, and the quickest way to solve them is to understand identity clearly. Once you grasp how UID, GID, EUID, and EGID fit together, you stop guessing about why access is denied, and you start predicting outcomes with confidence. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A Linux user account is best understood as an identity record that maps a human-friendly name to a numeric identifier used throughout the system. The numeric identifier is the user identifier, UID, and the kernel uses that number as the primary way to recognize who a process belongs to. This is important because names can change, can be duplicated across different systems, and can be formatted in ways that are convenient for humans, while numbers remain consistent and unambiguous within a system. When you create files, the file system stores the owner as a UID, not as a name, and when you run programs, the kernel tags those processes with identity information that includes a UID. A beginner misunderstanding is thinking that a username is the key, when the username is really a label for the UID. If you keep that straight, many odd situations make sense, such as files appearing owned by a number when a name mapping is missing, or two systems disagreeing about file ownership after a transfer because they assign different UID values to the same username. Groups exist for a similar reason, but their purpose is to represent shared access and shared roles rather than individual identity. A group maps to a numeric group identifier, GID, and files and processes can be associated with groups to enable collaboration and controlled sharing. Instead of granting access to many individual users one by one, Linux lets you grant access to a group, then manage membership in that group. This is both simpler and safer because you can review group membership and change it without rewriting file permissions across a file system. Beginners sometimes interpret groups as an optional feature, but groups are baked into the permission model in a fundamental way because every file has an owning user and an owning group, and processes carry group context as well. The group concept also reduces the need to use elevated privileges for everyday tasks, because properly designed groups allow users to do their jobs without needing broad administrative powers. Linux Plus questions often test whether you recognize that the right fix is a group membership adjustment rather than a permission change on each file. To make these ideas practical, it helps to look at the three-part permission model that most beginners encounter early: user, group, and other. For each file or directory, Linux tracks the owner UID, the group GID, and a set of permission bits that specify what the owner can do, what members of the owning group can do, and what everyone else can do. This structure is the reason identity matters, because permissions are not interpreted in isolation. They are interpreted relative to who you are and which groups you belong to. If you are the owner bits apply, and if you are not the owner but you are in the owning group, the group bits apply, and if neither is true, the other bits apply. Many permission puzzles are simply misunderstandings of which category the current user falls into for that file. Beginners often change permissions too broadly because they want something to work immediately, when the more correct move is often to align ownership and group membership so the intended rule applies. Understanding UID and GID as the reference points for these categories is the first step towards safe access control. Now we can introduce the idea of effective identity, which explains why the same user can sometimes do different things in different contexts. A process has a real identity, which usually reflects who started it, and it has an effective identity, which reflects what identity it is currently using for permission checks. The effective user identifier, EUID, is the identity used when the kernel decides whether a process can open a file, bind to a restricted port, or perform another privileged action. The effective group identifier, EGID, plays the same role for group-based permission checks. This is a crucial beginner concept because it explains why a program might run with more authority than the user who launched it, or why a process might have access to resources that appear off-limits when you try to access them directly. Many security features and many administrative designs rely on this separation because it allows controlled privilege changes without giving a user full power all the time. Linux Plus questions may describe a program that can modify a protected file even when the user cannot, and the correct reasoning often involves EUID rather than magical exceptions. A classic way effective identity matters is in the idea that some programs are designed to run with a different effective identity to complete a specific task safely. The goal is not to make everything privileged, but to allow a narrow action that requires higher rights while keeping the rest of the user experience constrained. When a process has an EUID different from the user's normal UID, the kernel uses that EUID during access checks, which can allow reads or writes the user could not perform directly. Beginners sometimes think this means the system is inconsistent, but it is actually the system being very consistent about which identity is used for decisions. The reason this matters for security is that changing effective identity is powerful, so the system needs clear rules about when it happens and how it is constrained. For exam thinking, the main point is to recognize that the identity attached to the process at decision time is what matters, not the name of the person sitting at the keyboard. Once you internalize that, you can explain many cases where access seems to defy expectations. Group behavior also has an effective dimension that beginners often overlook, because many people focus only on the primary group and forget that users can belong to multiple groups. When you log in, your session typically has a primary group and may also have a list of supplementary groups, and a process can carry that group context forward. EGID is the primary effective group, but supplementary group membership can also grant access to files where group bits are the deciding factor. This is why group design is so effective for collaboration, because a single user can be in several groups that represent different projects or responsibilities. A beginner misunderstanding is thinking a user can only be in one group at a time, which leads them to overuse the other permission category and accidentally open resources too widely. Linux instead expects you to use groups to shape access naturally, keeping other permissions tighter while allowing authorized groups to work. Linux Plus questions that mention shared directories, collaborative edits, or multiple teams often want you to think in terms of group membership and effective group context rather than in terms of giving everyone broad rights. Identity also shows up in the idea of system users versus human users, which can feel odd until you understand why services need identities too. Many background services run under dedicated accounts with limited permissions, not because they need a human login, but because the system wants to constrain what that service can access. A web service, for example, might need to read content files and write logs, but it does not need access to every home directory on the system. By giving the service its own UID and running its processes under that identity, Linux can restrict its reach if it is misconfigured or exploited. This is a powerful security principle because it reduces blast radius, meaning a compromise of one service does not automatically become a compromise of the whole system. Beginners sometimes interpret service accounts as clutter, but they are a key tool for least privilege design. On the exam, when you see a question about a service failing to read a file or write a log, it is often a hint that the file ownership or group permissions do not align with the service account's identity. Understanding that services are users in the kernel's eyes makes those scenarios straightforward. Another important identity concept is ownership versus membership, because these are different ways access can be granted and they affect how you should fix problems. Ownership is about being the single recognized owner of an object, and it is powerful because the owner category is direct and usually straightforward. Group membership is about shared access, and it is usually the better design when multiple people or multiple processes need to work with the same set of files. Beginners often respond to an access problem by trying to become the owner of everything, which can create long-term management issues and make auditing difficult. A better mental habit is to decide whether the resource should belong to a specific service account, a specific person, or a project group, and then align ownership and group settings to match that intent. That intent-based thinking mirrors how Linux permissions are structured, because the three categories exist to support different access patterns. Linux Plus often tests whether you can choose the right pattern, not just whether you know that permissions exist. When you think this way, you can explain why changing group ownership on a shared directory is often safer than changing other permissions to make it world-writable. To deepen the stat thinking you learned earlier, it helps to see identity as metadata that lives on both files and processes. A file has owner and group metadata, and a process has identity metadata including UID, EUID, GID, and EGID values that drive access decisions. When something fails with an access error, the fastest path to understanding is to compare the identity of the process with the identity requirements of the file. Beginners often look only at the file permissions and assume the bits are wrong, but many times the bits are fine and the identity relationship is what is wrong. For example, a file might allow group read access, but if the process is not actually in that group context, the kernel will not apply the group rule. Conversely, a file might be owned by a service account, and a user might assume they should read it, but the system is correctly preventing that because the user is not the owner and not a member of the group. The mental shift is to treat permissions as a rule that depends on identity, not as a standalone setting. Linux Plus questions become easier when you always ask which identity category applies before deciding which bits matter. Directories are a special case where identity and permissions become even more important, because directory permissions control traversal and name management in ways that confuse beginners. Reading a directory usually means being allowed to list its contents, while executing a directory means being allowed to traverse into it and access items within it by name. Writing to a directory means being allowed to create, delete, or rename directory entries, which is not the same as writing the contents of a file inside the directory. These distinctions matter because they show how Linux separates the rights to change names from the rights to change file content, and identity determines which permission category applies. Beginners sometimes see that they can read a file but cannot delete it, or they can list a directory but cannot open a file inside it, and they assume the system is inconsistent. In reality, the system is applying distinct rules for directory operations, and those rules are still mediated by UID and GID comparisons. Exam questions often use directories to test whether you understand that deletion depends on directory permissions and identity context rather than on the target file's write bit alone. If you connect directory rights to identity, those scenarios become predictable. Effective identity also matters because it explains why privilege can be narrowly applied without giving a user full administrative power across everything. Instead of a user always operating with the most powerful identity, Linux supports designs where a task can be done with elevated effective identity only when needed, while the rest of the time the user operates with their normal identity. This is not only safer, it is easier to reason about when you understand that the kernel checks EUID and EGID at the moment an operation happens. Beginners sometimes imagine privilege as a permanent badge you wear, but in Linux, it can be a contextual state attached to a process. That contextual state also means you should be careful about what a privileged process can access, because it can do more than you might expect if it inherits environment and file descriptors from a less privileged context. Linux Plus questions can hint at this by describing a process that behaves as if it has elevated rights even though it was started by a normal user, and the correct explanation is that the process's effective identity differs from the user's normal identity. When you can describe that cleanly, you show you understand the system's trust model. Groups also connect to practicality in everyday administration because they provide a scalable way to implement least privilege without turning everything into a one-off exception. If a directory is meant for a team, it makes sense for the group ownership of that directory to reflect the team, and for the permission bits to grant group access in a controlled way. If a service needs to write logs, it makes sense for the log location to be owned by the service account or by a group that includes the service and the administrators who maintain it. This kind of design prevents the common beginner move of granting broad other permissions just to make something work quickly. It also makes troubleshooting faster because the intent is visible in ownership and group choices, and you can reason about access without reading complicated documentation. On Linux Plus, the questions are often shaped around this logic, where the right fix is to adjust group membership or group ownership so that the group permission bits become meaningful. When you learn to treat groups as the primary tool for shared access, you also learn to keep user ownership for personal resources and keep other permissions for genuinely public resources. That separation is a mature access control habit that scales naturally. A final beginner-friendly way to cement all of this is to remember that Linux identity is not a vague concept. It is a concrete set of fields that the kernel consults over and over. UID and GID identify the account and its primary group, while EUID and EGID are the identities actually used for access checks when a process attempts an action. Supplementary groups add additional group context that can unlock group-based permissions without changing who the user is. Files and directories store owner and group as numeric identifiers, and names are simply labels for those numbers, which is why identity remains stable even if names change. When something fails, you can almost always explain it by asking which identity category applies and whether the file's permission bits grant the required operation to that category. This approach also helps you avoid unsafe fixes because you stop thinking the solution is always to open permissions widely, and you start thinking in terms of aligning identity to intent. The exam rewards that alignment because it demonstrates you understand Linux's core security model, not just surface-level syntax. By the end of this episode, you should feel comfortable describing Linux identity in a simple but powerful way that supports both troubleshooting and exam reasoning. Usernames and group names are human-friendly labels, but the system relies on user identifier, UID, and group identifier, GID, values to enforce ownership and access rules consistently. Processes also carry effective identity, an effective user identifier, EUID, and effective group identifier, EGID, are the values used in permission checks, which explains why some programs can access resources a user cannot access directly. Groups provide a scalable model for shared access and least privilege, allowing collaboration without opening resources to everyone. When you apply stat thinking to identity, you treat permissions as rules that depend on who a process is at decision time, not as isolated bits on a file. That mindset makes Linux behavior predictable, keeps your fixes safe, and gives you exactly the kind of clear, systems-level reasoning Linux Plus is designed to measure.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.